As some of you know, that we shared with many people our developments back in March of 2015 and on the stages of TED, and also in the journal Science, where we talked about the CLIP technology, continuous liquid interface production. And I think the story there, as Jim alluded to, had a lot to do with speed and a new approach to manufacturing or fabrication. And today I'd like to share with you an update of our work, and really want to emphasize what I think is the true breakthrough that we're focused on right now, and that's materials properties. And it's great that Jennifer gave such a super talk to kick everything off with this morning, related to materials. And so a lot of people have been showing some version of this bell curve, and this is one adopted from Geoffrey Moore in Crossing the Chasm, and talks about the fact that in many technology adoption cycles, that sometimes a crack will emerge in a technology adoption cycle or curve that becomes a real challenge because of a product really doesn't bring forward a breakthrough capability that can allow a majority of new users to adopt the technology and really fundamentally change strategically the landscape of a technology. And Geoffrey Moore, in his latest version of his book, makes a supposition that, in fact, 3D printing exists today in that chasm. And I think there's a lot to be said for that. And I think probably one of the most important aspects associated with that has to do with the properties of the part. At the end of the day, it's all about the part that comes out of the printer, and does it have the performance to be a final part in a particular application. And so we believe a lot in the sort of philosophy that you'll see a lot in the Japanese culture, especially great companies like Honda and Toyota, related to the three realities. And that is the idea of having a real part in the actual place under the exact situation. So Genba, Genbitsu, and Genjitsu, and having those characteristics associated with the performance is really critical. And this is an example of a part being printed in our printer. And so with this perspective in mind, we have been heavily focused on making final parts and trying to use that as a characteristic to cross the chasm. And these are parts that would have the right properties. And I've got some examples that I can certainly pass around here. These are materials that are fabricated. Let me just toss them, and you can just pass them around the audience here. I don't want to toss it. It's heavy. There's another one. But this is the kind of material that can have the sustained use in real applications. And we have parts. You saw an announcement by BMW driving around in Germany. We have parts driving around in the United States. We've been helping manufacturers actually get products out the door and helping them do that. And it's because of a material property like this. These are rigid polyurethanes that have the impact strength necessary to be a final part. And in fact, these are multi-component resins that can tailor properties, and we have the ability to tune the final properties of a material by tuning the various components of these polyurethane resins, tailoring the tensile strength, the impact strength, and the heat deflection temperature, the glass transition temperature. And so we have materials that have the ability to be in the cabin of a car or an airplane because of these kinds of impact strength that one has. And we can do these in all range of colors. This is an example of a CT scan of an electrical connector of a part made by one of our beta customers. And this part was actually made 2 hours after taking our printer out of the crate, making the part and then running a CT scan. And you can see the kind of intricate structures that one can make in an electrical connector. But what happens with this ability with a real material is you go well beyond fit. This allows one to have fit and function, or fit, function, and performance. And having a real material allows them to think about a low volume run without the tooling costs, very expensive tooling costs, associated with these kinds of electrical connectors, and be able to do that with the design out of a 3D printer or a tool that's able to make it out of real materials. So a great example there. So that kind of material, rigid polyurethane, those are important classes of materials. They're very similar to polyamides in a lot of ways, nylon-type materials. But here's another material, or we call it our semi-rigid polyurethane, but these have the performance characteristics of polypropylene. Polypropylene is one of those large volume thermoplastics that are often used to have characteristics of great flexural strength, flexural characteristics. Isotactic and syntactic polypropylene have too high of a melt viscosity to be very useful in FDM-like technologies. But here's a material that has the kind of properties of a polypropylene and allows you to have the kind of flexural strength for clips and clamps and living hinges like this associated here with CES. A kind of gimbal with 3 living hinges allows the material to be printed but have these kind of characteristics. I don't think there are many UV curable systems that have these kind of thermoplastic-like properties. Cyanate esters, really high performance material. Very few people actually know what cyanate esters are unless you walk into places like SpaceX, NASA, Boeing, IBM printed circuit boards. These are really high performance resins, materials that have a modulus of 4 gigapascals. And again, we can tailor the modulus, and we have materials with heat deflection temperatures well over 200 degrees Celsius. Right, that's approaching 400 degrees Fahrenheit. These are the kinds of properties, and I've got materials up here that you can see afterwards, that have the kind of properties that could actually be used under the hood, that have chemical resistance, thermal resistance, and is also sterilizable. And we have one of our partners announcing tomorrow, and associated with the JP Morgan Healthcare Conference, some surgical tools made from these kinds of materials. Elastomers. Elastomers are one of my favorite materials. I have a couple examples of elastomeric materials made in our system. I can toss these down. These won't hurt anybody. We can catch these. And one there. Good catches there. You can see great colors. You can beat the heck out of those. They've had tens of thousands of cycles on them. They're great elastomers. They have all the characteristics of a reaction injection molded polyurethane. You can see we can tailor their properties. This is what we would refer to as a happy ball versus a sad ball. And this is the damping characteristics, the kind of resiliency that you'd want to have in an elastomer, whether you're designing a basketball sneaker or kind of an inner ear structure that would have sort of 100 micron thick walls for hearing aid companies. And so again, the kind of real properties that you'd want in an application like that. This is one of my favorite slides. This is data from our partner, the Ford Motor Company in Ellen Lee. And this is a classic stress strain curve for materials. And these are their favorite highly used injection molded resins. And so you've got a thermoplastic polyolefin, you've got polypropylene, acrylonitrile butadiene styrene, ABS, and you also have a nylon 6 that's glass filled. And our materials can match the properties, not only match, but exceed the properties. If you look at these area under the curve, exceed the properties of these conventional materials, right? And not only the thermoplastics, but also the glass-filled polyamide. This is a cyanate ester that's unfilled, and we have a very high modulus material associated with that. And then our elastomer shown at the bottom. And so it's this kind of data that I think is essential for having the kinds of performance characteristics that one needs to cross the chasm. And so, in some ways, we've been trying to think, well, where do we stand in a community of 3D providers? And if you look at the kind of materials I just talked about, in many ways, you would choose maybe FDM and SLS for a part that you want great functionality, great performance. But you might choose SLA and perhaps PolyJet for surface finish and the like. And I think what Clip brings is a hybrid of both, where you can have great surface finish and great characteristics, but have the materials properties that one would associate with some of the other technologies. And so we think it's filling an important gap. And it doesn't stop there. We have about 11 resins for our current beta customers. We're constantly designing new resins and designing new reference states. You may have seen an announcement by Jeff Clark from Kodak a couple of months ago in their analyst meeting. We've got partnerships with Kodak. We're basically setting up an app store for resins. We've got 11 of our own resins, and we're open and working with others to develop additional resins. And they have a wide range of really important properties, whether they're water soluble, hydrogels, biodegradable, and the like. We think it's these kinds of characteristics, much the way Jennifer talked about this morning, that allow us to use resins for the clip process. And so with this performance characteristic, we think it's the kind of thing that's going to be necessary and useful to give a strategic new capability to allow the broader adoption of 3D printing and actually go to 3D manufacturing. We think that's the material properties and performance is essential. Some of you have seen some elements of this. The process we use we call CLIP, and the idea was could we have a continuous liquid interface while we grow parts, sort of a chemical approach to resin renewal versus a mechanical engineering approach. So what we do is we have a bottom-up projection system in the UV, a 385 nanometer DLP projection system. Our window is not only transparent to light, but it's permeable to oxygen. Oxygen quenches the free radical photochemistry that we use in our process. It maintains a liquid interface, such that when we couple the transmission of oxygen with the ability of projecting light across 2 dimensions, we create a dead zone that's on the order of 20 microns or so that allow us to raise the platform up, create a liquid interface that brings liquid in underneath, and it's really a software-controlled set of chemical reactions that allow us to build parts. And when we do this, this allows us to dramatically speed up the process. It allows us to essentially eliminate layers. We have an active surface that's constantly growing, and I'll show you data to support that, and allows us to open up delicate and advanced new materials like I just showed you. I don't want to go through, especially for this audience, the details of this process, but I'll refer to this paper we published in Science back in March. But suffice it to say, there's a lot of details, a lot of chemistry and physics that goes into this process that allows us to use software to control. We basically have a print button today. The software controls all the details, and the things that we're controlling during this process, and this is a video that was taken on the stages of TED, but the things that we're controlling involve things like the flux of oxygen, how much oxygen is coming through. We consume a massive amount of oxygen, and we can measure that. The light intensity, the dose to cure, the viscosity, how far the light penetrates into resin, so-called molar absorptivity. All those details come together, combined with geometry, that's rolled up into a model that the software calculates everything. And it runs the process directly. And so we're actually doing finite element analysis in the cloud, where we use Amazon Web Services and others with this internet-connected device to allow us to run these processes. And you can see the results of a part arising out of the resin. You'll see some resin aggregating on a part that needs to be washed off, and you'll see the final part evolved out of a thin reservoir of resin. What this allows us to do is to get a really great surface finish. This is out of a Viper SLA, classic sort of layered technology. This is the kind of thing you'd get out of our technology. This is one of my favorite images. These little ramps are made upside down. They're all printed at the same speed. And basically, we're illuminating a rectangle in the beginning. So imagine it's printed upside down, and in the beginning, the rectangle is very long, the image of the rectangle. And then what we do is we hold that image constant, and every 100 microns in Z will make the rectangle a little bit shorter, and then shorter again, and shorter again. And if you look on the edges, that's a staircasing from changing the length of the rectangle. Well, instead of changing it every 100 microns in Z, we could change it every 25 microns in Z, or every 1 micron in Z, because it's just electronically changing the image. Okay? They're all grown at the same speed. Okay? And what you see is this edge effect, and we can get down to an RMS roughness value of under a nanometer, really smooth surface finish. If you crack these open, there's no indications of any layers. But to really reinforce what we do differently, if you were to try to take a traditional 2D printing technology and you went from 100 micron layers to 1 micron layers, you would slow it down by a factor of 100, if you could make it. These are all grown at the same speed. It fundamentally changes the game, we believe. So we end up growing test patterns. These are dog bone test patterns. And it allows us to measure mechanical properties for our different resins. And for us, it's kind of like doing chemical synthesis right in the printer. And this allows us to measure mechanical properties. And what's notorious by traditional 3D printing technologies, where you have a layer-by-layer approach, it's actually 2D printing over and over again, that the mechanical properties become a function of the orientation of the object. When we grow parts this way, the parts are isotropic. Okay, there's no orientation dependence on mechanical properties. That's game-changing and very different, and allows one to think about making very complex geometries like this lattice. Jennifer showed some beautiful lattice structures this morning. Here's another example. Imagine if, as you're building an object, that the mechanical properties are changing depending on the orientation of a particular geometry. That's what happens in traditional 3D printing. But with this approach, mechanical properties are invariant with direction and allows you to use intrinsic material properties coupled with geometry to make final parts in the way you want them to be, okay? So this is fueling a lot of interest in a lot of different areas. We focus a lot in the automotive. It seems like Silicon Valley is the center of automotive technologies nowadays, and we're helping a lot of people move things forward. But to hold that digital thread from design, not only to prototyping, where you're focused on fit mostly, but from design to prototyping to manufacturing, where performance is critical. Doing the same thing for aerospace and having high-strength, lightweight materials. One area that I'm really intrigued by and what designers and engineers are going to do with this technology, and some of the work out of the University of North Carolina in my academic lab, are microscale structures. The tools in the microelectronics industry have driven Moore's law from 10 microns to 10 nanometers. And people try to use those etching technologies in microfluidics and inkjet print heads and try to fabricate very complicated things in an etching technology with wafers. This is costly and it's expensive, time-consuming. A wafer would take a month in a lab to fabricate. We can actually grow these parts in tens of seconds out of great materials and do some amazing things. And so this combined with the other technology is what's driving a lot of our interest and our focus at Carbon Life Sciences, where we're actually doing a lot of things in the medical world. And not only doing the micro-scale things, but doing the kinds of things you think about for the inner ear, and then you also think about the orthodontic space. And I'm not talking about just doing dental models, because you can do that with prototyping resin. But I'm talking about having resins with the properties that you can actually make the aligners directly. And having the requisite material properties to do that directly is the kind of thing that we can do moving forward. Here's an example of some work out of the University of North Carolina, the great North Carolina logo there. These are 6 different resins my former students have designed that are water soluble, printed with clip. But they're designed to be water soluble at different rates of dissolution. And you can see these dissolving over time as a time-lapse photography, such that these are being used in transdermal drug delivery technology for delivering vaccines and enzymes and other types of systems moving forward. So we have a big focus in medical and allowing to make very complicated structures, even changing the chemistry during the build of these kinds of microneedles for specific delivery of biologics, for example. So part of what we do is we work very carefully at trying to be proficient at the intersection of hardware, software, and molecular science. Silicon Valley has been really great at software. It's getting increasingly good at hardware and software. Think about home automation. But to add a complete new dimension, molecular science, is really hard. And we work very hard to focus on having people that can collaborate across these designs or across these disciplines. And it's an important part of who we are. And it's also an important part of what we're delivering to our customers today. And traditional manufacturing equipment has largely not changed in the last 25 years. People buy equipment. You have to typically do a manual software update. Now there's software being delivered via the cloud, data aggregation from your printer to make sure that what you're making on part number 1 to part 10,000 are actually aggregated and the machines are running optimally. There hasn't been a lot of breakthrough with the manufacturing equipment, and it's in this backdrop that we're very interested in future-proofing our customers. And so our printer is going out as a subscription model, and it allows people to never again be laden with an obsolete piece of equipment. The equipment is constantly upgraded, and one of the most important aspects of that is an over-the-air ability to upgrade software. So I drive a Tesla. I just got a big software upgrade, and we push software. We have a big push of our software out to our beta customers next week. We did one right before the holidays. Each of these software upgrades gives new capability and new ability to do things you couldn't do before, and it improves the performance of the printer. It also allows us to access new resins without having to purchase a new machine. And so every resin's different on how it prints, And that ability allows us to keep our customers at the cutting edge. These printers also stream a massive amount of data. And this data allows them to assure that when they're making things at part 1,000 versus part 10,000, that they're made under the exact same conditions. And so we have the ability of having that kind of data available. It also allows us to transform fundamentally how one does service and support. We can monitor these printers and make sure operationally they're in a tip-top condition as they fabricate, and the kind of thing you want actually in a manufacturing setting. So we have a great software team that is developing the prepare to print and the support technology and the software associated with that. This is just a little video running where we have our user interface where we drop in supports. We're eventually going to make the support software available to everybody out there as it improves, but it's a 3-second addition of supports to the parts, and it allows us to enhance the capability of the printer. We get a lot of data coming back. This is just an example. It's almost like a NASA control room where we have the data coming in from the field, much like Tesla has and the Tesla engineering systems. But the ability of understanding when the printers are up, when they're down, where LEDs are working, and when they're powered properly. Resin usage, you can see people really like the colored resins. You can see the star ratings, people score the prints. You can see in Red's prints that were underperforming. We get to take that data with their permission and enhance the performance and learn. So as we become proficient at being the leaders in manufacturing with light, it's this kind of data that drives the process. So we're pretty excited about a future fabricated with light and the implications that this can have in society. And I think upon reflection, if you look at what else has driven, what other technologies have been driven by light, and the most important arguably is the two-dimensional photolithography in the semiconductor world. Moore's law is driven by light. It's driven by patterning in 2 dimensions. And this is an enormous impact on society, hundreds of billions of dollars of GDP associated with photolithography in 2 dimensions. And the opportunity of taking this capability and going in 3 dimensions, I think is really transformative in how society does things and fabricates really complex things. I think it has profound impacts on where manufacturing is done, powering companies to be future-proofed, making very complicated things, and putting powerful tools in the hands of a variety of different people and organizations to do things. And arguably, having a $2.1 trillion field to play in is fundamentally a huge opportunity here that we and others are excited about. This is enabled by having the right team in place. I have been fortunate to be around of some of the most accomplished people in my career in academia. I can tell you I've never been around a more accomplished group than I am today. We've got 120 people in the heart of Silicon Valley in Redwood City. We've got 20-some people from Tesla. I've got the VP of engineering from Tesla, the head of software from Tesla, our VP of manufacturing from Tesla. We've got 11-year veterans of Google that were there in the beginning that did a lot of the early days of plumbing and encryption and Google Docs and other places. You'll see a couple Apple symbols here. We got people from Facebook and Twitter and other places. It's just an amazing team of people working together at the interface of hardware, software, and molecular science, and it's a real privilege to work with this group. And so with that, let me end, and I'd be happy to answer any questions if there's time.